The scheme shown above represents steps 18A through 22B of the second generation synthesis of C-nucleoside prodrugs from the Siegel paper that we read in class. It converts an amine to a biphosphoramide center using a two-step reaction. The first step of the reaction involves the addition of the amine to the phosphate via a deprotonation of the amine through triethylamine and the elimination of a chlorine ion from the phosphate. The second step of the reaction involves the addition of a nitrophenyl to the phosphate and the elimination of a chloride ion from the same phosphate. Finally, selective recrystallization using diisopropyl ether is utilized to influence the stereoselectivity of the reaction, resulting in a 39% yield. This product can then be used to create the final prodrug in later reactions.
The overall goal of the reaction was to produce the molecule labeled as 4B. Our steps of the reaction show the synthesis of 22B from 18A, which is important in the reaction since the rapid production of 22B allows for large quantities of 4B to be produced. Not only was 4B found to be the most effective for treatment, but it also has the largest yield, 69%, making synthesis of 22B preferable to the other products. In our scheme, the starting material was 18A. This molecule contained an amine group. Since the amine group is highly nucleophilic, it would have been more reactive than our ending product, 22B, since the nitrogen of the amine group would be in conjugation with the oxygens bound to the phosphorus, making nitrogen less likely to act as a nucleophile. In this scheme, we have created a nitrogen-phosphorus bond, an oxygen-phosphorus bond, and broken nitrogen-hydrogen bonds and two phosphorus chloride bonds, and created an R stereocenter at the phosphorus.
Reagents and conditions of this reaction, there's really kind of two parts to it. In the first step, triethylammonium serves as the nucleophile, and OP-OPHCl2 serves as the electrophile, and it takes place in a polar aprotic solvent of CH2Cl2. In the second step, 4-nitrophenyl serves as the nucleophile, and then the R chain connects to the OP-OPHCl. That serves as the electrophile, and this takes place in a solvent of triethylammonium. And And then in the last final step, IPR2O, which serves as the solvent, and that's just to reorganize the stereochemistry of the product.
For this part of the reaction, we want to isolate the final product, 22B. To do so, diastereomers have to be separated, which can be done through crystallization. This works because diastereomers have different physical properties. In this case, the difference in their solubilities in diisopropyl ether is being taken advantage of. The diastereomer that is less soluble will crash out of the solution first when cooling down.
The most notable detail of this reaction is that 22A is a diastereomeric mixture. This mixture needs to be purified to get a single diastereomer, 22B, as a product. For this to happen, 39% diisopropyl ether is added to the mixture to crystallize 22B. Selective crystallization of diastereomers works because diastereomers have different chemical and physical properties, unlike enantiomers. Because of this, they also have different solubilities in different solvents and can be purified. This technique is frequently used in toxicology because each diastereomer has different properties. So, in medicine, one diastereomer could have a good medicinal effect while the other could be toxic to a person. An example of this is dopamine. Its precursor, dopa, used to be used in a racemic mixture of two isomers D and L. The D form was found to be toxic, so now they use a selective recrystallization of diastereomers to purify and only use the L form in medicine.